47,000 engineering graduates. That's what China adds in a single week if you average its annual STEM output across its university system. The United States, in the same time frame, adds a few thousand, highly specialized, heavily filtered, and already pulled into corporate pipelines before they even finish exams. And yet the surprising part isn't the gap. It's what each country does next with that pipeline. Because raw output is only the first layer. What matters is conversion. Turning degrees into factories, research labs, chip fabs, energy grids, and defense systems that actually scale. And here the contrast becomes uncomfortable. China's Ministry of Education has spent 2 decades aligning universities with industrial policy targets, robotics clusters in Shenzhen, semiconductor talent programs tied directly to SMIC's supplier ecosystem, AI labs co-funded by state-backed funds like the National Natural Science Foundation. In 2023 alone, over 3.6 million STEM-related graduates entered the workforce, many already embedded in state-linked industrial zones before graduation. The United States, meanwhile, produces fewer engineers per capita, but filters them through a different machine entirely. Defense contractors, big tech, and research institutions like DARPA-funded university labs. The system is less centralized, more market-driven, and far more fragmented in how talent gets deployed. A graduate from MIT and a graduate from a state university in Texas might both end up designing similar systems, but they arrive there through entirely different pathways, with different incentives shaping what gets built and when. And this is where the real tension starts to form. Because if you only look at innovation metrics, patents, Nobel Prizes, frontier research, the United States still holds structural advantage. But if you look at production scaling speed, how fast a design becomes a physical system, China's engineering surplus starts behaving less like education data and more like industrial infrastructure. There's a detail most people miss. In several Chinese industrial parks, engineering graduates are not just hired into companies, they are assigned to clusters. Entire cohorts from provincial universities are funneled into the same supply chain ecosystems, meaning knowledge doesn't just exist in individuals, it accumulates geographically. In places like Suzhou's semiconductor corridor, a junior engineer doesn't enter a company, they enter a network. In the U.S., the equivalent engineer is more likely to enter a firm, not a system. That distinction sounds subtle until you realize systems scale differently than firms. Now, to be fair, the American argument isn't weak. Decentralization has historically produced breakthroughs precisely because it avoids bureaucratic locking. Too much coordination can suffocate experimentation. Silicon Valley exists because no one was centrally planning it. But here's where the contradiction tightens. The same decentralization that produces breakthroughs also slows replication. And in a world where chips, batteries, and AI infrastructure are scaling at industrial speed, replication speed starts to matter as much as invention. There's a quiet question sitting underneath all of this. Is engineering power in the 21st century defined by who invents first or who scales without friction? And if that question is even partially correct, then the gap between 5.4 million engineers and policy committees studying shortages isn't really about education at all. It's about what each system believes engineers are for, creators of novelty or engines of deployment. I think the uncomfortable part is that both models are rational inside their own logic. That's what makes comparison so unstable. But I'm not fully convinced we're measuring the right output variables yet. Because the next layer of this story isn't how many engineers exist, it's what happens when they hit the machinery of national priorities, and whether that machinery accelerates them or slows them down in ways we don't notice until it's too late. And the direction that answer points to isn't symmetrical. Suzhou is where the earlier idea stops being abstract. A graduate from a provincial engineering university in Anhui doesn't just get a job there. In the industrial parks around Suzhou Industrial Park, they are absorbed into semiconductor packaging lines, equipment calibration teams, and materials testing labs that sit only a few steps away from one another physically, and only a few minutes away in communication terms. You can walk from a photolithography supplier to a chip packaging facility to a testing lab without leaving the same controlled industrial zone. That's the part we touched earlier, engineering cohorts moving together. But the deeper mechanism is not social, it's structural. China's engineering pipeline has, over 2 decades, been increasingly shaped by policy documents, like the Made in China 2025 plan and the earlier 863 program, which quietly redirected university funding toward applied fields: materials science, automation, electrical engineering, and later AI. The Ministry of Industry and Information Technology doesn't just publish targets. It co-finances university labs tied directly to industrial parks. By the time students graduate, many are already inside a production ecosystem that knows what it wants from them. Take SMIC's Shanghai N+2 node expansion as an example. It's not just a factory upgrade, it is a recruitment engine. Entire cohorts from Shanghai Jiaotong University and Fudan's microelectronics programs are mapped into supplier networks before graduation. The engineer doesn't enter uncertainty. They enter a predefined function in a scaling system. Now contrast that with the United States. The U.S system is not missing engineers. It is dispersing them. DARPA funds at universities like Stanford or MIT often produce breakthrough-level research in robotics, chip design, or materials science. But once that research graduates into the real world, it fractures into competing firms. NVIDIA, Intel, Lockheed Martin, hundreds of startups that rarely coordinate with each other unless market forces force them to. The CHIPS and Science Act of 2022 was meant to address this fragmentation, allocating roughly $52 billion in subsidies and incentives to rebuild domestic semiconductor capacity. But even that mechanism routes through corporate competition. Intel builds one fab in Ohio, TSMC builds another in Arizona, Samsung builds in Texas. Each is its own island of execution, with its own supply chain logic, labor pipeline, and timeline. There's no single Suzhou. There are dozens of partially connected attempts to replicate one. And this is where the difference becomes less about ideology and more about latency. A system built around coordinated deployment reduces friction between idea and implementation. A system built around distributed competition increases variance, which can produce breakthroughs, but also delays convergence. Let me anchor this in a human scale. A junior engineer at Huawei's Shenzhen campus in 2024 described their first year not as learning the job, but as being assigned to a moving machine. Their team rotated through 5G base station optimization, then AI inference hardware testing, then network stability simulations, all within the same internal ecosystem. The expectation wasn't specialization in isolation, but adaptability inside a continuously shifting production stack. In a comparable American firm, say a mid-level hardware engineer at a Bay Area startup, that same year might involve iteration, but within a much narrower product boundary. Faster experimentation, yes, but fewer systemic transfers of knowledge across adjacent industries. One system compresses learning into networks, the other compresses it into firms. There's a small irony here. The United States actually invented much of the coordination infrastructure China now uses: DARPA-style program management, Apollo-era systems engineering, Cold War industrial mobilization. But after the 1,990 seconds, that model was gradually replaced by venture-scale decentralization. Efficiency gave way to optionality, and optionality, for a long time, worked. Here's a dry observation that almost sounds like a joke, except it isn't. The U.S built the world's most advanced coordination systems for getting to the moon, and then decided coordination was too slow for making apps. But the trade-off is now visible in sectors where scale matters more than novelty. Still, there's a gap in this comparison that we haven't closed yet, because high-volume deployment doesn't automatically translate into high-end innovation dominance. And the data, when you look closely at frontier patents and core semiconductor IP, refuses to line up cleanly with simple engineer counts. That tension is where this story starts to get less comfortable, because it suggests both systems are optimized for different futures, not competing for the same one. The problem with comparing engineer output like a scoreboard is that it quietly assumes all engineers are interchangeable units of capacity. They're not. In 2023, China produced roughly 4.7 million STEM graduates, depending on how you count engineering-adjacent degrees. The United States produced closer to 820,000 across comparable categories. The gap looks almost absurd on paper, until you realize that only a fraction of those graduates in either country end up working in core industrial engineering roles like semiconductors, power systems, or advanced manufacturing. And this is where the story bends. Because the real constraint is not how many engineers exist. It's how many engineers can be absorbed into high-complexity systems without bottlenecks forming elsewhere. Supply chains, capital equipment, regulatory approval, or managerial depth. China's system has an advantage in absorption speed at mid-complexity manufacturing scale. But when you move up to frontier nodes, EUV lithography ecosystems, leading-edge GPU design, or aerospace-grade materials, the bottlenecks reappear. Not because of talent scarcity alone, but because those systems depend on extremely narrow choke points. ASML's EUV machines, EDA software from Synopsys and Cadence, specialized chemical precursors, and decades of iterative IP stacking. And here's the reversal that often gets missed in simplified comparisons. The United States doesn't win by volume. It wins by controlling bottlenecks that sit above volume. Take ASML's EUV lithography machines. Each unit costs over $180 million and takes years to assemble. Only a handful are produced annually in Veldhoven, Netherlands. Without them, sub-7 nanometer chip production simply doesn't scale. The U.S. doesn't manufacture these machines, but it influences critical upstream components. The optical design IP, the resist chemistry research, and parts of the supply chain tied to American and allied firms. So even with fewer engineers, the U.S. ecosystem concentrates talent at choke points rather than across the entire production landscape. But that creates its own distortion. Because when you concentrate talent into bottlenecks, you also concentrate decision delay. In 2022, multiple U.S. semiconductor fab projects experienced delays not due to engineering failure, but due to permitting, environmental review cycles, and funding disbursement timelines tied to federal and state coordination. Intel's Ohio fab, initially projected for mid-2020s operation, has seen repeated timeline adjustments as construction, labor, and supply constraints intersected with regulatory sequencing. This is not inefficiency in a simple sense. It is institutional caution layered on top of distributed authority. And caution scales poorly when global competitors are optimizing for execution speed. Now zoom back to China. There's a tendency to assume that higher engineer volume automatically equals faster technological convergence. But even within China's system, there is internal friction. Provincial disparities matter. Coastal industrial hubs like Shenzhen, Hangzhou, and Shanghai move at a completely different speed than inland provinces, where talent retention and industrial integration are weaker. The 5.4 million engineers figure hides uneven distribution that looks more like clusters than a uniform wave. One engineer working in a Shenzhen AI hardware lab described it as running on rails, but the rails don't always connect to the next station. You can move fast, but only within the segment you're assigned to. That matters when innovation requires cross-domain collision. And this is where both systems start to reveal their hidden vulnerability. China can scale execution quickly once a direction is set. The U.S. can generate direction quickly, but struggles to scale uniformly. One optimizes for convergence, the other for divergence. Neither is neutral. There's a moment in economic history that mirrors this tension. Japan in the late 1900 seconds. Massive engineering capacity, world-leading manufacturing discipline, extraordinary coordination between MITI, Keiretsu groups, and universities. But when the system hit frontier-level innovation transitions, especially in software and platform ecosystems, its structure struggled to adapt. Not because engineers were lacking, but because reconfiguration speed was lower than global transition speed. Now, I'm not saying the same trajectory repeats. The conditions are different, the scale is different, and China's integration between state planning and industrial deployment is far tighter than Japan's ever was. But the structural question is similar. What happens when a system optimized for scaling meets a phase where scaling depends on technologies it doesn't fully control? There's another layer here too, one that rarely gets discussed in policy reports. Engineers don't just produce output, they produce feedback loops. The way they are distributed determines what problems get noticed, funded, and solved. And right now, those feedback loops are diverging so sharply between the two systems that they may no longer be solving the same category of problem at all. Which raises a more uncomfortable thought. We keep comparing capacity, But capacity for what exactly? There's a point in every comparison like this where the numbers stop behaving like explanations and start behaving like signals we're interpreting too confidently. We've been treating millions of engineers as if it automatically maps to industrial power. But the system underneath decides whether those engineers become acceleration or just organized employment, and that distinction is starting to matter more than the headcount itself. China's advantage is still visible in one specific place: the speed at which intent turns into physical output. If Beijing sets a direction, EV supply chains, high-voltage grid expansion, semiconductor packaging, or AI infrastructure, the engineering layer underneath tends to align quickly through provincial coordination, industrial parks, and state-linked financing channels. The feedback loop is tight. But tight feedback loops have a hidden cost. They can amplify direction errors just as efficiently as correct ones. If the target shifts, the system has to reroute millions of embedded roles that were never designed for independent drift. The United States sits on the opposite configuration. It doesn't align quickly, but it also doesn't lock in easily. An engineer in Austin, another in Seattle, and another in Boston can all be working on adjacent problems without ever being part of the same system architecture. That fragmentation slows execution, but it also allows local corrections without waiting for national consensus. So the real divergence isn't capacity. It's correction speed versus execution speed. And both systems are now entering a phase where their historical advantages are being stress-tested by the same pressure: AI-driven industrialization cycles that move faster than policy design ever did. Here's my opinion line, and I don't say this lightly. Neither model is currently optimized for the pace at which frontier technologies are now compounding. One is too coordinated to pivot quickly. The other is too dispersed to scale consistently. But I'm not fully certain that this tension resolves in a clean convergence. It might not. There's a more uncomfortable possibility that the world doesn't converge on a single best engineering system, but instead splits by domain. One system dominating scale-heavy infrastructure, the other dominating invention-heavy frontiers. Not because of ideology, but because physics of organization doesn't allow one structure to win everywhere at once. The doubt I keep coming back to is this: are we misreading coordination as strength in one case and misreading fragmentation as weakness in the other? Or are those exactly what they are, just optimized for different phases of technological evolution? We tend to assume the future rewards a single dominant model. History is messier than that. The Cold War didn't produce one winning industrial logic. It produced parallel systems that outperformed each other in different categories until the categories themselves changed. My prediction is narrow but deliberate. Over the next decade, the gap we talk about won't be who has more engineers, but whose engineers are closer to the bottlenecks that define the next critical technology stack. That's where power is quietly relocating, away from labor supply, toward control points in energy, compute, and fabrication. And if that's true, then today's comparison between millions of graduates and committees studying shortages is almost the wrong conversation entirely. The real question is who is placing their engineers inside the parts of the system where a single breakthrough can multiply into everything else. Because once you see that layer, the numbers stop being the story. They become just the inventory.